Hello and welcome to our virtual Lunch and Learn. Today we are talking about mechatronics. My name is Rachel Green. I'm the Digital Communications Specialist here at McNaughton-McKay Electric Company, and presenting for us today is Nolan Van Wormer, Integration Engineer at our Madison Heights, Michigan location. Out in the comments section today, ready to answer your questions, is Tom Joy, Systems Engineer, also out of our Madison Heights location. We will also have a Q&A portion at the end of Nolan's presentation for him to answer your questions in more depth. We'll be getting started shortly, but we'd like to allow a few minutes for attendees to join us. As you come in, let us know where you're tuning in from in the comments section. Hi, John from North Carolina. Thanks for joining. As we continue to socially distance, we're happy to be able to host these live sessions here on YouTube, making it possible for you to join us from the comfort and safety of your own homes and offices. You can view recordings of previous virtual Lunch and Learns on our YouTube channel under the Virtual Lunch and Learn playlist, and we will be continuing this series every Wednesday at noon, so be sure to join us on your lunch break going forward. For anyone just joining, welcome to our virtual Lunch and Learn. Let's talk about mechatronics. Let us know where you're joining from in the comments section. We will be looking for your questions as you have them while our presenter, Nolan, covers best practices when selecting components for a system, as well as some common pitfalls to avoid. Our specialist, Tom Joy, will do his best to respond to your questions in the comments as we go along. And we'll also have a Q&A segment at the end of Nolan's presentation to address some of those questions in more depth and to allow some time for any follow-up questions you might have. If you'd like to reach out afterward, or if you're watching this as a recording later, you can send us an email at macandmaclive@macmac.com. We'll be sure to pass along your question to the presenter, so just let us know which session you attended so we can get that to the correct presenter. We'll have the email address on the screen for you at the end of the session as well. All right, it looks like we have a few attendees now, so let's go ahead and get started. Nolan, I will pass it over to you now.
Yeah. Thanks, Rachel. Hi, everybody. Thanks for joining us on your lunch hour here. So we're going to talk a little about mechatronics, what that means to your machine, what that means from a Mac perspective, and how we can work together to use mechatronics for you. So I'm Nolan Van Wormer. I'm a systems engineer out of Madison Heights, Michigan. So let's get started. So we'll go through what is mechatronics, why to use it, application considerations. We'll go through an example, and then we'll use the Rockwell Automation sizing tool motion analyzer to go through a full system. So jump right in. What is mechatronics? You can see on the screen there. Big long word. Basically, it's bringing the mechanicals department and the controls department together for the benefit of your machine safety, function, save you time, save you money, and reduce your risk from the machine perspective as well as safety perspective. So typically what we see is the mechanical department takes their application data, whatever the loads is, whatever the cycle time is, starts picking out some mechanical components that look right in the design, that have a good enough safety factor, maybe consider life, maybe not. Pick some gearing to make an inertia match, or maybe not, and pick a motor. And then a few weeks later, once the designs come along, the controls guys get kicked off, they pick out a PLC, some safety components, start designing a panel, and drop a drive in. And then we hope that that drive and that motor work together for a functioning system. So the mechatronics approach takes that a little bit differently, and we get the mechanical team and the controls team together from the start. We look at the application, what's the load, what's the cycle time, how do we optimize that, look at safety factor, look at safety of the system, make sure we have a good inertia match, that we have the latest PLC, the right drive and motor optimized for whatever you're going for. Do you need washdown rated? Do you need safety? Are you trying to reduce costs, reduce weight, whatever it may be? We look at it as a whole system, mechanical and controls together. That's really what mechatronics is all about. So why to use it? So with more and more competition for you and your customers going after the same kind of machines, want to make sure that whatever you're offering has the most features or is the most cost competitive, or whatever it is your selling point. And everyone's trying to build machines faster. Job start dates keep getting pushed back, but job delivery dates don't. So you want to make sure that whatever you deliver is going to work as seamlessly as possible. No one's ever had a situation come up where that tooling that we told you was 1,000 pounds, it's 1,500 pounds now, and we need to move it in 2 seconds instead of 3 seconds. Never happened to anybody ever. And pretty frequently when that happens, you end up with broken gearboxes like we see in that picture right there. Designs changing after products have been ordered. Something got heavier and you need to make a change to the structure. You need more linear rail or more of some component or different size of something. All things we want to avoid if we can up front, or knowing that when that design change does come, that you can make the change of product easily, know what the limits of your system are. And then as things change, sometimes boxes don't fit anymore and you got to make adjustments. And having a system up front where you know what the limits are and how big everything is and what you have to work with makes making those changes a whole lot easier. And especially with everything going on in the world right now, lead times can be all over the place. And with our team, we can look at changing various components, working with our long list of different vendors to get you the right product in the right amount of time. So some more benefits of Mechatronics, relying on engineering resources at McNaughton-McKay. We have a whole team of people dedicated to looking at the mechanical system and the control system together as one. We can offer CAD models. We know what the system limits are. A little bit later, we'll get into a report we can offer that shows you, based on what you tell us for speeds and loads and your environment, it can tell you what the speed limits are, what the torque limits are, what you should set in the PLC. We're up on the latest technology to offer you advanced safety features. We can help you get to market faster, speeding up your design, providing you CAD models and recommendations on product. And we can reduce cost by optimizing the system as a whole. And we'll get into an example showing how much cost we can really take out of a system. So we talked a little bit about optimizing at the beginning. What does optimizing mean? It can really mean a whole bunch of different things. It can be optimized for size. You're limited in some package of something you're trying to replace, or the whole tool needs to be small. It can be optimized for cost. Everyone's always trying to take money out of their job, put more money into your pocket.
Nolan, I think we lost your audio there. Bear with us, folks. I think we've lost our audio. I apologize, everyone. Give me just a second. I'm going to try to reach Nolan. I think our audio has cut out and he's unable to hear me as well. So give us just a second and we'll get back online here. I hear something. Are you back?
I'm back now. Okay.
Great.
Sure
I think we
there.
missed a few of those bullet points. So if you can back up just a little bit for us.
Okay. It's talking about what optimization means for you and your system. I see all the bullet points on the screen. It can mean any number of different things, as well as trying to plan for things that you shouldn't really have to plan for. You know, going from 60 jobs an hour to 75 jobs an hour. Your system's underperforming, all things like that. So lots of different things we can optimize to, not always the same for every machine or every application. So we'll move on here. Things we consider and things we look at when we take a systems approach. So there's quite a few things that can be common misconceptions. A lot of people forget about accel and decel time. You think if I'm moving 40 inches per second, that if I go 40 inches, it's going to take me a second to get there. Well, you got to remember you have to get up to speed and you have to stop once you get to position. So you got to look at your profile where you are ramping up, cruising, and ramping down. So with a 1/3 trapezoid profile, which is what's shown here, what you end up with is actually 1.5 times your average velocity as your peak speed. Definitely something you want to make sure you consider. So it requires a higher velocity. And also, as you change this accel ramp, say you're limited on the peak velocity based on what you estimated, then you have to accelerate harder, which is going to take more torque. And then a very common thing to overlook is e-stop time. So it's not designed for upfront in the sizing. And then once the machine gets to the floor, you set the e-stop time to whatever seems right. And it could be way more than the gearbox can handle and end up with a broken gearbox like we saw a couple slides ago. Another thing to clarify is accuracy and repeatability. We see some different options there, which we'll talk about in a second. So we have, do you need to be repeatable or accurate in one direction, or do you need to be in both directions? So is your advanced position critical and your return is just getting out of the way, or do you need to be accurate in both directions? Are you moving horizontal or vertical? This makes a big difference on the tooth loading and if there's backlash or not as you're moving vertical, and then compliance in the system as well. Let's take a look at our bullseyes here. So the one on the left there, low accuracy, high repeatability. So in a servo system, if you are accurate but not repeatable, you can adjust your set point. If you're very repeatable but you're not accurate, you can adjust your set point and bring those stars into the center, like we see in our second bullseye there, to become accurate as long as your system is repeatable. So if I need to go to 12 inches every single time and I keep going to 12.5, I'm hitting 12.5 every time, you can adjust your system back so that 12.5 becomes 12, and we hit that high accuracy, high repeatability. Getting to that high accuracy, high repeatability often comes with more costs, whereas a repeatable system that might not be as accurate that you can tune in with your adjustments on the control side can save you some money in your gearbox and other components. And then we have some other applications where I don't need to be terribly accurate or terribly repeatable. We can go with a much lower cost system. So just understanding the difference between accuracy and repeatability goes a long way in optimizing cost and other components. So talking about backlash. So you see here, backlash is this gap between these two teeth here, where as you change direction, there's some lost motion. So if we look at a low-cost economy gearbox, is going to have the backlash shown there. You have a couple arc minutes, and then an elastomer coupling can have a lot of squish within the spider insert. So that can end up being a 1/2 degree at full load of a particular gearbox, which can be quite a bit of motion. So if we want to look at something that's a little more rigid, you get a high performance gearbox that has a bellows coupling, so there's no rubber inside to flex, it's solid metal. We can take that whole 1/2 degree out and we're left with fractions of a degree. And you can end up with a 1/4 inch of lost motion on a 60-inch trunnion at full load, which can be a huge amount of error build up. So if you have trunnions and those types of products, you want to make sure that you're picking out the right gearing that's going to give you optimized performance for your system. Other thing that you want to look at is machine life. If an actuator is rated for 1,000 pounds, what is that speed that it's rated for? What's the life it's rated for? A lot of times we look at graphs like we see over here on the left where as your stroke increases or your speed increases, you want to derate the actuator to be able to get their desired life. For ball screws and bearings, very similar charts exist, as well as we see kids jumping rope there. That comes from if you run a ball screw too fast or a long screw too fast, the screw itself will turn into a jump rope and you'll get a bunch of wobble and a bunch of whip, as it's called, and it can totally destroy your bearings and it'll greatly decrease the amount of life you get out of that product. So you want to make sure you're aware of what the critical speed is if you're using a screw type product, so you avoid your screw looking like that jump rope and damaging your product. Other things to consider is the efficiency or friction of whatever product you're using. Here we see an old rusty machine screw. So what we're looking at is the difference between a ball screw and a machine screw. So a ball screw is going to have ball bearings where you have rolling friction. It's going to be a lot more efficient, a lot easier to turn. But on the flip side, if you have a vertical load, ball screw is much more likely to backdrive under its own load, so your load will drift down. Where in a machine screw, you might want that inefficiency. So finding that balance of where you need efficiency and where you don't to achieve performance of your machine. So let's take a look at some things we look at and how we collect data. So when we do a sizing, our drives motion mechanical team, we look at what the load is, what your move profile is, how often you're cycling, any other specifications for your actuator. Do you want a rod style actuator? Are you looking for a belt? You're looking for a rack and pinion? Do you have a similar machine for? What type of drive and motor family you're looking for? Do you want the latest and greatest technology? Do you have a huge install base of legacy equipment you want to try and stay within? Is there a safety factor you're looking for? Is it 2 or 3x, or you're doing an aerospace type application, 5x, something critical? So all those things, we collect them within our application data sheet. And then we have a report, which I can pull up now. So once we collect that all that information, we go through all of our sizing. We can provide you a report that looks like this. So it's got your information, whoever worked on it, when we worked on it, what your job number is, so you can put it within your job file. We tell you what voltages we assumed, what environment we're assuming. We have all the application data for life. We have spots for notes there for you. And for each individual axis, we have all the notes of what load we sized to, what e-stop time we allowed for, what the total cycle time is, some notes on what the motion profile is, show you a little picture of what we get out of the sizing software. You know what your repeatability and accuracy you should be expecting. And then we'll give you all the information on the products that we help select, how it's loaded, what it's rated for, give you a utilization percentage to know how oversized, if you need to speed things up. If there's installation manuals available, we'll attach those in the report here, give you maintenance manuals so you know how often to lubricate and how to take care of your machine. Same thing there for a gearbox, how much of the speed are we using, how much of the torque are we using, notes on that particular gearbox is lubed for life, give you information on the Rockwell motor we select for your particular application, what it's rated for, how much it weighs. Other important notes like the VPC motor has a 230 volt fan that you're going to need to plan for. And then to help out the controls folks that are on the call, once you get to the programming side of things, it'd be really helpful if you knew what the mechanical team picked out and how that impacts your controls. So we set up a chart here that'll walk you through your motion axis configuration. You put in your drive, your motor, here's all the scaling information. So there's no guessing or having to go ask, go look it up. It'll be right there for you. How to set up auto tuning, all your loops, position limits, acceleration limits, velocity limits, all those things. And then our legal disclaimer there at the end. So we'll jump back into the PowerPoint here. So that's kind of our process. We collect all that data from you and then report back what we sized to and what everything looks like. So what does that look like for a system that we've done for a customer? So a while back, I did this application. We had an elevator. It was a dual rack and pinion drive. We were lifting 500 pounds, 76 inches in 6 seconds. Customer already had designed in a 10-to-1 gearbox and a 7.5-inch pinion. So we went through, did a sizing, and then I asked, do you mind if I play around with those ratio and that pinion a little bit to try and optimize the system? We'll take a look at what the customer originally came up with. So we ended up with a 165 millimeter frame VPL motor with the biggest Kinetics 5500 drive available. And that gearbox that they had picked out, at 10-to-1, we were actually exceeding the RMS torque. So the continuous torque of that gearbox, we were exceeding based on the duty cycle they were running. Look at that total system add up, because we're looking at the whole system. It's more than just the motor and gearbox. It's motor, gearbox, drive, motor cables, circuit breakers, everything that goes in the panel. Total cost, looking at about 11 grand for that solution. So if we optimize it and we go to a smaller pinion and put more ratio into the gearbox, we're able to get that system down to about $7,000, taking 37% of the cost out. We end up with a better inertia ratio match. You'll have an easier time tuning the system. It'll be more responsive. It'll perform better. We were able to drop down to a 100 millimeter frame. That's dropping 3 motor sizes. We dropped 2 or 3 drive sizes. The gearbox actually did get smaller because we need less torque with a smaller pinion. So the whole system becomes more efficient from a power usage perspective, as well as we're not overloading any one component. So the system overall performs better and costs less. So now we'll jump into what it looks like a motion analyzer system, which is where this screenshot came from here. So some of the features before we get right into the software. You have a lot of flexibility in units. So if your mass you have in pounds, but your strokes in millimeters, software doesn't care. There's drop downs for all that stuff. We can size VFDs or we can size servos. The profile you import, you can actually export to the PLC. So if you have a complicated move profile, you can export that as a CAM table and import it right into the PLC. You see performance of each of your components, not just the Rockwell components, but also some of the Encompass partner products. We can look at what your energy consumption is to be able to compare different solutions for total power draw, so what it's going to cost in the long term for the end user. You can play with different gear ratios and a lot of different things to try and optimize the system for you. So let's take a look at a sample application here. So we'll take a 500-pound load. We're going to move it 24 inches in 3 seconds. We're going to do horizontal. And so we're going to put it on some profile rails. And we're going to press and hold 2,500 pounds for 10 seconds. We'll retract in 3 seconds and dwell for 5. Really want to make sure it's as small as possible and as cost effective as we can get. So we'll probably go with a screw type actuator for something like that. Keep the package small. So you first launch your motion analyzer software here. We'll go in, we're going to size and select rather than just looking for pricing on something where you want to put a bill of material together. So we said we're going to go with a linear load. So we'll pick the linear load tab there. We'll go ahead and put in our load mass in pounds. We had 500 pounds. And important thing to note, a positive force opposes positive motion. We see that in our picture here. We'll be a little conservative with our linear rails and say we have a 0.1 coefficient of friction on that horizontal surface. So then we're not going to put our applied force in here because it's not always on the load. We'll add that in our motion profile because it's only on certain parts of the segments. So we say we're going to, if you just have a basic, I need to make one trapezoidal move and then dwell, you can use this. Otherwise, we'll click more options to give you a more extensive profile editor. We'll go ahead and delete that, and we will add an index here. So we're going to move, so 24 inches in 3 seconds. Okay, and then once we get there, we have a couple options. We can leave it as a typical 1/3 trapezoidal move with a 1 second XL. If we want to change that, we can change to a trapezoidal move. And then we have control over our XL rate. If we want to take a longer XL or we want to bring it down to somewhere in the 1/2 second XL range, we can take a look at that. And then we'll add a dwell. So this is where we're going to hold for 10 seconds. We'll press and hold for 10. And here's where we're going to put it in our 2,500 pounds of force. And then we need to retract. So we'll add an index. And we can actually copy this one. Go back to that one we just added, paste it, and flip it. So now we've retracted, and we said we had a 5 second dwell. So we'll put in our 5-second dwell. And you can see what the position graph looks like. We went up, we cruised, and we came back down, and we're waiting in our retract position. You can look at the acceleration graph. So if in our graph we want to add some S-curve to make our whole move look a little smoother, maybe get rid of some of the jitter in the extended and retracted positions as we're coming into final position, we can put something like a 30% XL jerk, and you see that ramps our acceleration up and down. So when you're first starting and you're breaking away all that stiction, you're actually ramping your acceleration up. Makes it a whole lot easier on the mechanics, and we'll do the same thing on our way down. So we see here, we are ramping the acceleration up, and we're ramping the decel up and down. So we'll leave one S-curve, and we'll leave one without. So that's what our profile looks like. So we'll move over into picking out our mechanism. So we said we're going to go with a ball screw style actuator. So we'll start with went ahead and pulled some specs from one of our vendors. So our lead is going to be a 1/2-inch lead on this. I already have the inertia here. It's in inch pounds squared. Go ahead and grab that. And we're going to assume a total efficiency of 90% for that particular actuator. Then once we have that selected, this particular actuator, because we are worried about overall length, we're going to use a reverse parallel option. We put all of our inertia already in the mechanism, so we don't need to add it in here. We'll go ahead and jump along here. We're going to use our new VPL motors with their single cable feedback. And with that, we're going to use the Kinetics 5500 drive. This is a 480 volt system. And then we'll let the software do the work from there. It goes through and does a little search. All right. So within our one-to-one kind of solution, we see we're only using about 1200 RPM of this particular application. And within the biggest frame size VPL, we're limited. We're using quite a bit of the continuous torque. We should probably upsize that drive a little bit, reduce some of that. So that motor's getting pretty hot out there with the duty cycle we're running. So because we're only using 1200 RPM, I see that as an opportunity to change that belt ratio to a 2-to-1, stretch that speed range out here to around 2400 RPM, and we can probably use a smaller motor if we do that. So let's go back into our transmissions tab. We'll edit this, and we'll change that to a 2-to-1. Again, we don't need to play with the efficiency or the inertia there. We accounted for all that on the screw side. But in going to the 2-to-1, we are going to go back to our inertia. The 2-to-1 has a different inertia. We'll make that update there. And then we can go back to our selection and search again. So we had a 165 frame motor there with the biggest size drive. If we do another search again, we can come up with some smaller motors here. Let's take a look at this one here. See how that looks. So wants us to use a little drive there. The catalog is going to recommend an HO40 drive for that particular motor. So we're able to drop a motor frame size, reduce our temperature of that motor. We're only using 2/3 of it instead of upwards of 80%, up near that 2400 RPM range. So taking advantage of the speed range of the servo instead of just being up near the peak torque, we're going to extend that speed range out and use some mechanical advantage of the actuator to lower our torque needed. And then we can go into configuring our axis. We can tell what kind of encoder we want, build out a full part number. We want a multi-turn encoder. We'll go with a keyed shaft. We don't need the shaft seal kit or anything like that. We'll go with a network safety drive. Pick a motor or cable that's put a 10-meter cable on there. Once that's all configured, we can go into our power supply and make sure we're not going to regen too much energy or anything like that. Being that we only had 500 pounds, most of our power went into pushing the load, not regenning or when we were decelling. But we can, if you were to have that, you can do a shunt search and evaluate if you need a shunt, saying that our internal shunt can totally handle whatever we're throwing at it. This is where we can see where our voltage is rising and falling as we're running. This isn't a terribly demanding application. It's mostly in that press and hold where we're not using a lot of speed. So we can see the energy you can put in, how much current you're using, what electricity costs in your area, how often you're running to get your total cost. And we can configure our power supply. If we have multiple axes, we can chain them all together and pick out all of the connectors we need, all the line filters, circuit breakers, anything like that. So if we wanted to do that, we would add a power sharing drives group, and then we'll drag this axis down in there. We can actually just duplicate this axis. So we'll copy it and paste it into here. So now we have two axes within this, and we get the option for, are we AC sharing or DC sharing? So given that it was a pretty low power application, we could probably get away with one drive powering the whole system. And we'll just bring AC into the first drive, and we'll share DC across the rest of them. So we see that probably will be good. So then we can do a search here. We'll calculate the utilization and see that the converter section of that first drive can more than handle the power supply for all of it. We don't need to add a capacitor module or anything like that. Then we can configure our bill of materials. We want to share control power with both drives, so we'll add that in there. We'll add the line filter. We'll add a circuit breaker instead of a fuse. Then once we have all that put together, we can go into our bill of material, and we see all of our connectors. We see our motors and cables for each of those and all the drives. So that is what Motion Analyzer desktop tool looks like. So this is a tool free to download from the Rockwell website. It is no longer updated, so you're only limited to the VPL series, and the Kinetix 5500 is the latest product. If you need to use the VPC motors or the 5700 drives, Rockwell does have a web-based tool, Motion Analyzer Online, for you to create an account there. Some of the benefits of using that tool is we can collaborate on a system. So if you start a project on your own and you want to share it with one of your McNaughton-McKay systems engineers, happy to take a look at a system that you started, or we can complete the project for you and share it with you so you can see kind of how we did things, what it's sized for, all within the software. Rachel, did we have any questions come up during my presentation?
We do not have any live questions at this time.
Okay. Well, let me switch back to the PowerPoint then. So that's what we came up with. So within that particular axis, you'll see we were able to, by really taking a full system approach, reduce the size of the motor, reduce the size of the drive, which is going to save some money on the whole bill of material side, as well as benefit the end user. So if there were no questions, anyone watching this after, feel free to reach out to us, and happy to help you size your system in any way we can. So, thanks everybody for hanging out with me for your lunch today.
Thank you, Nolan. That was a great presentation. Thank you to Tom Joy out in the comments, being our resource there. And thank you to all of our viewers for your time today. Like Nolan mentioned, you can reach out to us with any questions if you're watching this as a recording later at that email address, macandmaclive@macandmac.com. Just be sure to let us know which session you attended so that we can direct this to Nolan and he will respond to you directly. Wonderful. Thank you again for joining. Remember to subscribe to the McNaughton-McKay YouTube channel for more industry content, and we look forward to seeing you live again soon. Thanks so much.